If you have ever solved dynamic programming related problems, you know that these are the hardest problems to solve. And the challenge comes that when exactly we know that this problem is related to dynamic programming, and whether or not in this particular scenario we should apply dynamic programming or not. So for that, I have developed several patterns that you can use in order to recognize and to solve the problem using the dynamic programming approach. The first one is, I call it quintessential bottom-up approach. So what's that mean? What's the main obstacle using the bottom-up approach is to visualize the solution. And what I mean by that. So when we have a dynamic programming problem, so what we do is we are taking a problem and we are breaking down to smaller subproblems, and then we are building up to our solution. But we are storing our temporary results, our subproblems. We are storing either in array or in two-dimensional array, and it's not clear how exactly we are going to store them. It's hard to sometimes to visualize how that the array or two-dimensional array would look like. But in case of the quintessential bottom-up approach, that array is already given, array or two-dimensional array is already given as a part of the requirement. So for example, let's take this example. So we need to find how many unique paths moving from the start to end, from the right to the down, right? So from moving from here to here, how many unique ways? And there are, for the rows, right? For this row, the values are, there is only one way that we can go. We can either move right or down, right? There is only one way to go there. So we can go always right, right? So there is only one way, and for the column, it's also the same. So we can always go down, and we are populating these values 1 and 1. But how about for this cell? For this cell, we can come from the top or we can come from the left, right? So we are taking the sum from the left and from the top, which gives us 2. And for this one, we are taking again from the left and from the top, 3, 1 plus 2, and the 3 plus 1. So we are populating this row, and we are populating the next row, and after that we are returning our result, which is 28, right? Again, in this case, it's very easy to apply the dynamic programming approach, because in this case the two-dimensional array is already given as a part of the problem, right? As a part of the requirement. So code-wise, how would it look like, right? Again, code-wise, what we do is we have a 2 for loops, and in the first for loop, so what we are doing here, so for the first row and the first column, we are populating the values with 1, and for all other rows, we are taking the whatever value at the top and whatever the value from the left, the value from the left plus the value, this one is value from the left and this one value from the top, right? So that's how we are solving this problem using a quintessential bottom-up approach. Let's go on to the next one. Another one is, like, for example, let's say that we need to move from start to end with the minimum sum, right? So from the right, or so move from the start to end with the minimum sum. And then we are given for each cell, we have a value, right? So we have 1, 3, 1, 1, 5, and so on. And then we need to find the way how to move from here to here with the minimum value, right? So what we do is here, so what we are doing here, right? So we are, again, we can move right or down, right? So if we are moving right, so we are just, there is only one way to go here, and so the value will be 1 plus 3 is 4, 4 plus 1 gives us 5, so we are populating these values, right? How about this one, right? So we are again populating 1 plus 1 gives us 2, 2 plus 4 gives us 6, so we are populating first row and the first column. And after that, for this one, we are doing exactly the same as we did in the previous one, but with the one exception is that here we are taking this value plus whatever the minimum in here and here, right? So we can come either from the left or we can come from the top, right? 5 plus 2 gives us 7, and the 5 plus 4 gives us 9, so we are taking 7, and so we are populating and we are returning this result. Again, in this case also, it's a quintessential bottom-up approach, so we cannot solve this problem with any other. We can solve, of course, with the other approaches, but the best way and the easiest way to solve this problem is to use bottom-up approach dynamic programming, because in the requirement we are already given that array or two-dimensional array. In both of these cases we are given an array. So let's go, and in the code-wise, right? In code-wise, what we do is we are taking So we are taking the value of the current cell, and we are creating another two-dimensional array. So we are taking the value of the current cell, and we are creating two-dimensional array. We are storing our subproblems, right? So we are taking whatever the minimum, either from the left or from the top, and we are adding for the value as a value of the current cell that we have seen above, right? That we have seen here. For example, in this case, we are taking the value from here 5, and whatever the minimum value from here, or either 2 or 4, right? So we are taking 2 and we are assigning to this cell value of 7. Okay, this is another example of the quintessential bottom-up approach. And let's go to the next one. In the next one, in this example, right? So we are given an input, but it's not clear, but it's not exactly we are given two-dimensional array, but we can easily create a two-dimensional array in order to store our subproblems given the input. So for example, in this case, we are given an array, and we are given an array of the binary numbers string that represents the binary numbers, right? So 1 0 0 0 1 and so on, and then we need to find the largest subset of the array such that there are at most m zeros and n ones, right? So which means that we need to take from this array a subset that will give us that will have at most m's and at most n's, right? So for that, so what we do, so it's obvious that we need to consider the all scenarios, and we need to solve a subproblem and build up to our solution, right? So what we do here is we are creating two-dimensional array. We are creating a two-dimensional array, and here x-axis represents n, right? And the y-axis represents m. So we are creating two-dimensional array. Also, we are adding zeros here for the first row and the first column, because to represent the cases where we have a 0 n's and the 1m and the vice versa, right? So I have a full solution for all these problems on my channel, and I will also include that in the description for this problem or for the previous problem, for the problems that we have already seen, right? So again, so what we do after creating an array, the solution is pretty straightforward. So what we do is we are considering each string for all of the subproblems. Again, for the solution, I will include that. For the full solution, I will include that in the description so you can check. This is the 3 example of the quintessential bottom-up approach. Again, in this case, the either array or two-dimensional array is given as a part of the requirements, or we can easily create an array or two-dimensional array to store our subproblems, as in case of this largest array, or as in case of this largest subset of the array, right? So in this case, it's very easy to create a two-dimensional array looking at these values, right? We are in the m, so we are in the x-axis, we will have n, and the y-axis we will have m, and we are going to store the subproblems in the two-dimensional array. Next set of problems is called the string problems. So these are basically related to the manipulation with the string. So for example, one of the classical example is find the longest common subsequence. If we are given two strings and we need to find the longest common subsequence between these two strings. In our case, it would be A, C, E, right? So we are removing B and D from the text 1, and we get the ACE as the longest common subsequence. How we are solving this problem? So as you can see here, we are creating a two-dimensional array where we are storing our temporary results, right? But the difference between the string problems here, between this pattern and the quintessential bottom-up approach, is that in this case we need to come up with the structure, right? We need to come up with the two-dimensional array or an array or some other data structure where we are going to store our temporary result. So what we do is for the visualization, right? So we are creating to make it more visually understandable, we are creating a two-dimensional array here, and in that array, in the x-axis we are storing the text 1, and the y-axis we are storing the text
2, right? So the first row and the column, we are populating that with the zeros in order because we will use that as a part of the solution. So what we do is we are solving a smaller subproblems, and then we are going to solving the smaller subproblem, and then we are going using that subproblem that helps us to solve the bigger problem, right? So we are building up to our solution. So for example, first we are solving a problem for the a and a. If the a is equals to a, then we are adding 1 here, right? So then we are comparing. How about the a b, right? A is not equal to b, so we are taking the value from here, right? So at this point, for the a and the b, so what we are going to take is we are going to take whatever the highest value, which value is the bigger, right? Either from the left or from the top, right? So let's take this example, right? For example, here, let's say that we are solving a subproblem AC and the ABC, right? So we are solving this subproblem. So is C equals to C? Yes, C is equals to C, so which means that we have at least one character here, right? If we are taking C and the C from the equation, so what it means? It means that we need to know that what is the longest common subsequence for A and the AB. But we have already solved that subproblem, right? So we have already solved that subproblem here, so we are taking the value from here, right? So now let's go to the next one. Let's say next one is that the AC and the ABCD, right? D is not equal to C. So if it's not equal, then it means that we are not adding any new character to the equation. So what we do is we are taking whatever the maximum is, A, B, C, D, or A, C, and the ABC, right? Either this one or this one. So we are taking whatever the maximum is one of these, right? So in this case, we are taking the maximum here is 2, so we are taking 2 here. And the solution wise, if we look at the solution, right? So what we are doing, right? If they are equal, so if in this case, right, if the C is equals to C, so what we do here, if the C is equals to C, which means that we have at least one character here plus whatever the maximum value. So we are taking C from the equation. So now we need to know that the longest common subsequence for A and the AB, right? For A and AB, we have already solved that subproblem. So we have solved AB, so now we are going to the next level, right? ABC and AC. So we have already solved that subproblem, and then we are taking the value 1 plus whatever the value is here, right? So when they are equal. When they are not equal, so what we do, right? We are taking the maximum value either from the left, in this case, right, in ABCD or AC. We are taking the maximum value either from the left or from the top. Now let's go to the next one, right? In this case, the next one is the edit distance. In edit distance, it's the same. So we are given two values, word 1 and the word 2. And so we can, in either of these words, so what we can do is we can remove, update, or replace the character. And then we need to find out how many of those changes we need to make in order to, until these two words are equal, right? So what we do again here, we are solving using the same approach. So what we do is we are creating a two-dimensional array where we are storing our two words, right? In the x-axis we have rows, and in the y-axis we have rows, and the y-axis we have the horse, right? The word horse. So what we do is, so the first case, right? So when both of these strings are empty, then in that case we need to make 0 changes. If let's say that the word 1 is empty, then for the word 2, so what we are making 1, 2, and the 3 changes, right? In order to make them equal. And if the word 2 is empty, then in that case we need to make 1, 2 for each character. We need to make a change, right? So we need to add a character. So we need to make 5 changes in order for them to be equal. And that's the
That's the base case. Now we are starting to solve a subproblem, right? The first subproblem is we are comparing h and r, right? Is h equal to r? No, they are not equal. If they are not equal, so we are taking one of these values from here, right? Either whatever the value is minimum, right? If when the both of them are empty, when we have r and the word 1 is empty and we have h and the word 2 is empty, the minimum here is 0, so 0 plus 1 gives us 1. But let's take another example. Let's say that we are at this position, right? We are at the position HO and the RO. HO and RO here, right? So in this case, so what we have is O is equals to O. Yes, O is equals to O, right? O is equals to O. So it means that we have, if they are equal, so which means that we don't need to make any changes at this point, right? We don't need to make any changes because O is equals to O, and then we need to find that what was the minimum, what was the value of for the h and r, right? So for this subproblem, what was the value, minimum changes that we need to make for this subproblem, h, r, and the minimum value is 1. So we are taking that value to here, right? So now for the RO and the HO, we need to make only one change here, right? We need to either replace H or either replace R, and we will have two equal strings. So solution-wise, again, so what we are doing here, right? Solution-wise, we are checking that this is for base cases, for when one of the strings are empty, and if the characters are equal, then we are just taking the value from here, right? As we have seen here in the case of the RO and the HO. So we are just taking the value from here. And if they are not, so we are adding, so which means that we need to make one change. We need to make one change, and we are taking whatever the minimum value in one of these cells, right? Either from the left, from the right, or from this cell, right? So from this cell, either from the left, right, or from this cell. So we are taking the minimum, whatever the minimum value. The next one is that let's take a look at another problem, which is also string related problems. Again, for all of these problems, I have them in my channel, and I will include them in the description. The next one is that the longest palindromic subsequence. In longest palindromic subsequence, we are given a string, and we need to find the substring that is the palindromic and the longest. So for example, in this case, the longest palindromic subsequence is B, 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 and the B, right? So what is the palindrome? Palindrome is that if for backwards and forward, the strings reads the same. So for example, in this case, if we remove A backwards and forward, it reads the same. And also in this case, what we need to do, right? So we can remove the letters, but we cannot change the sequence. So we cannot shuffle the letters around. So again, what we are doing here, right, in this problem, so what we do is we are using two-dimensional array, and we are in the x-axis and the y-axis, we are using the same string, right? So what we do here, so first one, we are solving a problem for each letter, right? So for example, in this case, we are solving for each letter, for first letter, second, third, and so on. So we are solving if, let's say, we have only one letter. If we have only one letter, the length of that longest palindromic subsequence is just 1, right? Now we are solving for 2, right? So for example, for the index 1 and 2, for the index 2 and 3, for the index 3 and 4, and so on. So we are comparing those, and we are storing, for example, let's say for index 0 and 1, right? So for the 0 and the 1, for this one, right, 0 and the 1. So B is equals to B, so we are storing B is equals to B, so the longest palindromic subsequence is 2, and so on. So we are populating these values. And so what we do, right? So for the case, well, let's say that we have solved for when the size is equals to 1 first, when the size is equals to 2, then when the size is equals to 3, and when the size is equals to 4, right? Size is equals to 4. there are only 2 substrings that the size equals to 4, and at the end we are storing when the size equals to 5, right? So what we do is we are comparing for when the size equals to 5, we are comparing the first, right, and the last element. If the first and last element is true, right? So which means that we have at least these 2 as a palindrome, right? So we have to our palindrome we are adding at least 2, and we are taking whatever the maximum for this subproblem, right? Starting from the index 1 to the 3, right? So starting from index to 1 to 3, so we are taking whatever the maximum value from the subproblem that we have already solved. So for example, in this case, what we have, right? So if they are equal, then we are taking the +2 because they are equal. The edge indexes are equal, and we are taking whatever maximum in the middle. That's the first one. But if they are not equal, right? If they are not equal, so what we are taking? We are taking either maximum of this one, right? So either maximum from 0 to 4, right? Either a maximum from 0 to 4 for this subproblem, or from the 1 to 5, right? So we are taking 1 to 5. So again, what we are doing, we are creating 2-dimensional array here, and the x-axis and the y-axis is represented by our string, and at each step, so what we do, right? At each step, we are checking. At each step, so we are checking that if our edge letters, if they are equal, then we are taking these 2 letters, and whatever the subproblem that we have already solved, so we are taking, so in between, right? In between there could be like a 100, let's say we have only 3, but let's say we have 100 letters in between, right? So at this point, when we are solving the problem for our whole string, we have already solved this subproblem, right? So we are taking whatever the maximum substring we are getting from here plus these 2, right? So plus these 2, and if they are not, then we are taking, for example, for 5, we are taking from 0 to 4 or from 1 to 5, right? So whatever maximum, so we are taking, and we are populating our 2-dimensional array. And next one is word break. In word break, what we have is we are given a string s, and we are giving the word dictionary. So what we need to find out is that can we, using these words, can we make up this string, right? The given string, and we can use every word as many times as we want. So for example, in this case, we can make up a word using the words from the dictionary. So we can use apple once and once, and so since we have apple, we have and, we are returning true, otherwise we are returning false. So how we are going to solve this problem? In this case, we are creating not 2-dimensional, but we are just creating an array, right? So we are creating an array, and in the array, so we are, for each letter, right? So we are creating an array with the size of our string +1, right? I'm going to explain exactly why we are using the +1. So we are creating here array, as you can see, for each index, starting from 1 to the last index. So we are creating array with the size of apple, so with the size of our string +1. So what we do at each step, so we are solving this problem in 3 steps, right? At the first step, so what we do, we have an I index, right? So we are moving our I index, and we are checking that against, at each index, we are checking that against each words that in our dictionary. So we are checking that, for example, let's say we want to check it against the apple, right? So we are moving our I, and at this point our length I is equals to 2. So we are checking that is I is equals to word length. If it doesn't equal, so it doesn't make sense to compare, right? So because let's say that the word is at this point is only the size of 2, but the shortest word that we have is 3, so we are skipping that, right? So let's say that we are at this position, so we are going to all the way to the apple, right? So we are checking here the first check, right? So we are checking that if I is equals to word length, right? If I is equals or more than word length, yes, it is, because in this case for the apple,
And for the and also, it's more than the word length, right? So that's the first condition. And the second condition, what we are checking here, we are checking that at this point, right, for the DP, we are storing all the values, right? So we have already solved the problem for the index 1, 2, 3, 4. So we are checking that the if I minus word length, if that is true, right? In order for us, right, in order for us in this case, right? So in order for us for this apple to consider that as a part of our solution, so we need to make sure that whatever the letters that come before, right? So whatever, let's say, let me give you this example, right? So let's say that we have also another apple prior to this apple, right? So in order for us to consider this apple as a part of the solution, that apple that apple also should be in our dictionary, right? So that's why we are the first index. We are creating the first index. We are setting that to true, and because it will help us eventually to solve the problem. I think let's go up to the end. You will understand why this true exactly matters here. So we are checking that if dp I minus word length, if that is equals to true, in our case it is. So what we do then, we are going and checking that the last one, right? Last one is that we are taking the whole word here. Whole word is apple, and we are comparing that if that is equals to our word. In our case, yes, it's equals to apple, so we are setting that to true. So again, we are setting that to true, and we are going for the next one, right? For the A, for the N, and we are going for the last one, D, right? Now we are at the D, at the last index. Now again, we are checking against all our three steps, right? It passes the first step. Now let's go to the second step, right? In the second step, so we are checking that the if dp I minus the word length, which means that the minus length of the and, if that is true, because for us to consider and, right, it means that the apple, this part, right, apple, should be also part of the solution. It should be also in our dictionary. That's why we are setting the true here, and that's why we are setting the true for the zero index. And if any other word that comes to prior to the apple, so we should solve that subproblem also to make sure that that's also in our word dictionary. If let's say that there is another let's say there is another word prior to the apple, let's say that the or, right? So or is prior to the apple. So if or is prior to the apple, what it means that it cannot be, so we cannot set that true here, because that or, right, that or is not in our dictionary, so that will not be our solution. So that's why we are setting the first one here to true, and we are setting to true here. And for the and, again, we are comparing that, okay, is it really dp minus word length, is it equals to true? Yes, it's equal to true. And we are going to the last one. Again, we are comparing word with our substring I minus word length. So we are taking this substring and then comparing with the word. It's true, and we are setting that to true, and at the end we are returning this last index. So the solution wise, right, so what we are doing here, so what we do is we are going over for each, we are moving our I, and at each step we are comparing against our words, right? So we are moving I, and at each step we are comparing for each word. If the I is, again, all three conditions, right? If the I is more than word length, that's the first condition we need to pass, because the length of the word should be at least more than the so the word that we are taking at the moment, where the I index is placed, it should be at least more than the word length. And the second condition is that if that the prior word that came before that, right? So if that is true, so we can consider that index, right? So then the next one is that we are checking that if these two passes, then we are just checking that if our word is equals to that substring. If it is, then we are setting that to true, and we are breaking at that point, right? So because we found that word, specific word in order to set our DPI to true. So the next one is that the interleaving strings. In interleaving strings, so what we have, right? So we have two strings, S1 and S2, and we need to find out whether or not we can make another string
S3 using the S1 and the S2, right? So, and we can use them in any order. So we can use, for example, any amount of the letters from the S1 and any amount of the letter S2, but we need to make sure that we cannot change the order. So for example, here we cannot change the order, and we need to make sure that we can make a string S3, right? So for example, we can take first from the first one, from the S1, for the second one, second letter we can take from the S2, for the third we can take from the S1, and so on, right? Whether or not can we make up using the S1 and the S2, you make the S3, right? So how we are going to solve this problem? So the first one is that, again, we are using two-dimensional array here. So we are using, so for in the x-axis we are using S1, and the y-axis we are using S2, but we can use them in any way we want, right? So we can, for example, use that vice versa. So we can use S1 in the x and the S2 in the y. And what are the steps, right? For the steps, so we have the first one, the base case, right? For the base case, we are checking that if the S1 and the S2 both are empty, so that then the S3 also, so in that case, S3 also has to be empty, right? So we are setting this value for the 0 and 0, so we are setting this value to true, right? So we can always make from the S1 empty and the S2 empty, we can make always make the S3 empty, right? So for this base case, we are setting as a true. Then what we are doing, right? So for the first row and the first column, we are going and we are checking that can we make from the S1, just from the S1 and or just from the S2, can we make the S3 directly, right? So we are comparing the first letter of, so we are comparing the first character of the S1 to the first character of S2, second character of the S1 to the second character of S2, and so on. So we are setting these values here, right? So for the first one and for the second one, here we are setting this value to true. Initially, when we create a two-dimensional array, all these values we are setting to false. But when we're starting to compare, when we are doing that for the first row and the first column, we are setting this value for the A, and because A is equals to the first character of S3A, so we are setting this value to true, right? So now we are going and populating our two-dimensional array. And the first one, so what we are doing, right? So we have populated a first row and the first column. Now let's go and take the first case. Let's take the first case of 1 and 1, right? So 1 and 1, which means that the one character from here and the one character from here. So we are taking they should be whether or not they are equal to, so this character and this character. So whether or not we can make an interleaving string using the first character from each and the two character from the S3, right? So for the case of 1 and 1, what we are doing, right? So we are checking that the last character that we have here, right? Last character is C, right? So we are comparing that if C is equals to one of these characters, right? Is C equals to this scenario, right? If C is equals to A, or is C equals to C, right? Yes, in this case, C is equals to C, right? So for 1 and 1. For this one to make sense, for this one to be true, so we are checking either one of them, right? Either one of them is equals. So we are checking that if A is equals to C, or if C is equals to C. C is equals to C in this case, right? So what it means? It means that if C is equals to C, then in that case, we are checking that for this makes sense, then 0 and the 1 and the 0 in this case, right? 1 and the 0. So this one should also be true, right? So the only way this one will work if that the 1 0 is true if C is equals to C. If that is not, if that's not the case, or another scenario is that A is equals to C, then in that case 0 and 1 should be. So then in that case, either this one should be true and the A is equals to C should be true,
or another scenario, right? C is equals to C, and the 1 and the 0 is equals to true, right? So since in this scenario is both are true, we are setting this value to true. Let's go to the 2 and 1. I think that will be more clear what exactly we are doing here, right? So for 2 and 1, so what we are doing in the 2 and 1, in the 2 and 1, so we are taking 2 and 1, right? 2 and 1, so which means that the which means that the 3 characters, right? In total 3 characters, 2 and 1. For the 2 and 1, what we are comparing that if the b is equals to b, right here, or b is equals to C, right? If B is equals to C, right? If B is equals to C. So we are comparing this scenario, right? If B is equals to B or B is equals to C. B is equals to B, this B is equals to B. For this one to make sense, A and C should be, let me revert it back. So A and C should be true, right? So since B is equals to B, 1 and the 1 should be also true, right? So 1 and 1 in this case is A and C, right? A and C is equals to true. That's why we are setting this value to true, right? And we are doing that for every combination. We are doing that for 2 and 1. We are doing that for 2 and 2. We are doing that for 1 and the 2. And so slowly we are building up to our solution. Again, as a solution wise, right? What we are doing here. So we are comparing, again, so we are starting from the 1 and the for A and the J. So at each step, we are checking what? We are checking that. So we are checking what? We are checking that if the character at S3, right? If that equals to our, so we are comparing that if that character is equals to our character at either S1, in that case, then the prior value, right? The prior value I minus 1j should be true, right? If that is true, we are setting that true. Or another case is that if the S2 character is equals to our S3 character at the moment, then in that case, the j minus 1, right? The same way that we have seen that either, for example, in case of the 1 and 1, either dp 0 and 1 should be true, or dp 1 and 0 should be true, and we are populating our value here. That's all. That is the last one that I wanted to use as an example to explain the string problems. So now let's revisit, right, what we have learned. We have learned 2 patterns here. The first one is the quintessential dynamic programming. In the quintessential dynamic programming, in the problem statement, we are already given the two-dimensional or an array or two-dimensional array, right? So it's very easy for us to build up to our solution. But in the string problems, as you can see, is what happens is that we are just given a string, and it's not easy right away to come up which exact data structure we are going to use in this particular scenario. For example, especially for interleaving strings, so you need to think about that. You need to think about what could be the right way to approach to solve this problem, specifically for all of these problems, right? Whether or interleaving strings, or let's say that the longest substring, or similar kind of problems when we need to use the dynamic programming. So we need to think about what exactly our data structure would look like, right? So which in our case, we're just only using an array. We can also use the hash map, by the way, but mostly we are using an array, right? So how exactly our array would look like in order to store our subproblem. So that's the biggest challenge when when you are solving these problems, right? So now let's go to another pattern. Another pattern is that I call it optimization, maximize or minimize, or game theory, right? So whenever you see a problem, we need to find the maximum value or minimum value, or we need to maximize or minimize our solution, or that is somehow related to the game theory. So we are going to talk about that in a bit later. So that is problem, that's optimization problem. In that case, we are again using the dynamic programming. We are given a days and we are given a cost. So basically, we need to buy a ticket for each day. So for example, if we are buying a cost for the 1-day pass, let's say that we are in a resort and we need to buy a ticket for the 1-day pass, right? So for the 1-day pass, we are paying $2. And for the 7 days, let's say if we are buying the 7 days, then in that case we are we are spending $7, and for the 30 days we are spending $15, right? Let's see how we're going to solve this problem, right? Again, in this case, we are using we are using a bottom-up approach, and we are creating an array where we are storing our subproblems, right? So smaller subproblems. So let's start from this. So we are creating an array with the size of the whatever the days that we have plus 1. So I'm going to explain why we have the j here, and we have 2 pointers here, I and j. So what we do, first we are moving our I pointer. So we are moving I pointer for the first day, right? Let's say that we have for the day 1, day 4, day 6, day 7, 8, and the 20, right? So what we do is for the first day we don't have any option, right? So we are only solving for the that subproblem. So for the first day, what we do, we are buying only 1 ticket for that day. So okay, we are paying $2, and the next day we are going for the 4th day. Again, we are spending $2. So then now we are going to the next day, right? So next day is 6 days, so we are paying again $2. Our total cost is now $6. Now we are going to the next one. Next day is for us what? Next day is 7th day. So again, we are paying it $2, and our total cost now 8. Our total now 8. Now let's stop at this point. So we have moved our I pointer. So what we do is now let's just go backwards and reconsider that can we do better than that, right? So what we do is we are moving our I pointer to the point when it's 7th day, includes the 7th day, right? So from the 1st to 7th. So we are moving our I pointer, so our j pointer here and our I pointer here. So we are taking the difference. The difference gives us what? 7 days, right? 7 days. Now let's consider this scenario, right? Now let's take the price that we are paying so far, which is DPI at this point, or take the value that we have at this point, DPJ, right? DPJ plus whatever cost we are, cost 1. Cost 1 means that for 7 days, right? Because we moved 7 days back. So either what we are doing in this case, right? Either we are paying $8 for each pass, or what we do is we are paying for 7 days plus cost DPJ, right? Why we are considering this scenario? Because let's say that we are moved also in the second case, right? So we are going to move our j pointer. Our j pointer we are going to move here. So we need to consider whatever comes prior to that, right? We need to consider whatever comes prior to that. That's why we are keeping our j pointer here. So we are starting from the 0, and we are adding one additional cell at the beginning of the array. So again, what we are doing here, right? So we are taking DPI, this value, or we are taking DPJ plus whatever we are paying for the 7 days. And now we can see that this one is more efficient, right? This one gives us 8, 0 plus 7 gives us 7. So we are replacing this value with the 7, and we are moving our j pointer to I pointer. Now they are at the same position. Again, we are moving our j pointer. Now we are going to go up to the end of the array. Then again, we are going to for the 20, right? So we are going to do the same exercise that we did for the 7. So for the 15 days, right? For the 30 days, we are going to do the same exercise, and each time we are going to recalculate. We are going to recalculate the minimum price, and at the end we are returning whatever the value we are getting here. So as you can see here in this scenario, right, specifically we are using we are creating one additional array where we are storing our subproblems. I think that when we put everything into the context, right? So when we review all these, the reason why I'm making this video in the first place, that if you are looking at all these problems, all of them together, it makes more sense how exactly, so you get more of sense how exactly you should approach to solve this problem. For some of the problems, let's say that for quintessential bottom-up approach, right? So what we have here, so we are given an array, and we are either given an array or two-dimensional array, so we can just start right away to solve those. So use the array that is given to us as a part of the requirement, as a part of the input to the problem, so we can start to solve the problem. For the other one, for the string manipulation, right? So whether or not to find the longest substring, to find the longest palindromic substring, and so on. So for those problems, we need to create an array, two-dimensional array, which is the which is not easy to come up all the time, right? So you need to put extra effort in order to exactly know that what array we are creating here to store our subproblems. And another one for the optimization. So whenever you see the words minimum cost, maximum cost, minimize or maximize, this is or game theory problems. They are the problems that are related to the dynamic programming. And again, what we are doing here is we are just trying to apply either bottom-up approach or top-down approach, right? So far we have been applying the bottom-up approach because it's easier to solve these problems, specifically these problems that we are reviewing using the bottom-up approach. So again, if we look at the full code looks as we have discussed earlier, right? So we are having two passes, right? One pass for the 7 days and one pass we have for the 30 days, and we are keep updating our value, and at the end we are returning whatever the minimum value what we have. So let's go to the next one. Next one is the jump game. We have several jump game related problems. Let's take a look at them step by step, right? One by one. So let's first start with the jump game, the first kind of problem. In this problem, so what we have, right? So we are given an array, and each index in that array, value of that index represents how many steps we can go, how many steps we can jump starting from that index. For example, in this case, from the index 0, we can jump 2 steps, right? 1 and the 2. And starting from the second index, we can jump 3 steps, right? And starting from this index, from the second index, we can jump 1 and so on. And then we need to find the minimum number of the steps that we are making in order to, we are making in order to reach the end of the array, right? So how we're going to solve this problem? Again, we are using bottom-up approach, and we are creating an array with the same size of our nums, right? So we are not creating here any extra cell. So we are starting from the very beginning, and for each cell, we are by default setting the value of the maximum. So in Java, for example, it could be integer max value and the similar, right? So, and also we are creating 2 pointers. One pointer is pointing from where we are starting, right? So from which position are we going from? And the J is maximum steps, right? How many steps, how many maximum steps we can go starting from that position, right? So for example, let's start from the first one, right? So how many steps does it take to go to the first one, right? So we are starting from the first one, it's 0, so we can update this value to 0, right away. So now let's let's move our I pointer, because we can move 2 steps. We are going to the next step, and then the next step, what we are taking, right? We are taking dp current value, right? Whatever the value is here, dp I plus j, right? I plus j, whatever the current value is here, which is what? Which is the value at the 1 is maximum, right? At this point, so maximum, or so the current value is I plus j, which is 0 plus 1. 0 plus 1 gives us the maximum value, and the new value is dp I, which is dp I, where we are coming from, right? Plus 1, because we are making 1 step here, right? So this one gives us 1, this dp I plus 1 gives us 1, and the current value gives us what? Current value gives us maximum, right? Maximum integer value. So we are taking minimum of it, we are updating this value. So again, we can move from the first one, right? We can go 2 steps. Now we are moving our I pointer also again here to the second one. Now we are going to start. So now we are going to the next step, and we are starting for the next one. We are starting from the second position, right? From here. Again, we are applying the same formula here, right? So what we are doing is we are taking the dpi plus j, which is that takes the maximum value, or we are comparing the dpi, which is where we are starting from. We are starting from here, and the value here is just that we made the 1 step. 1 plus 1 gives us what? Gives us 1 plus 1 gives us 2, and the dp value at this point is what? Dp value I plus j. I plus j gives us, we are taking the maximum value here, so maximum, we are comparing with the 2, and we are updating this value to 2. So it should be 2 here. And we are going up to the end of the array, and at the end we are returning whatever the minimum result. Now let's go to the next one, right? Next one in the jump game. So again, as you can see here, for each step, so what we are doing, we have 2 pointers, I and the j. So we are taking we are progressing, and at each step we are taking whatever the jump I that we have there. So at that step, how many maximum steps that we can make, right? Maximum jump. And we are starting to reevaluate and set the value. So we are taking 2 values, current and the new, and we are updating our value at that specific point in our DP array. So now let's go to the next one. Then in the next one, so what we need to do here, what we have, right? So we are again given an array, and we are given a starting position in that array. So for example, in this case, the starting position is 5. So which means that the 0, 1, 2, 3, 4, 5. So we have a starting position here. And what we need to find out is that can we reach an index where the value is equals to 0, right? So at each step, so what we can do, we can either jump to the left or right to the value of that position. So for example, if we are starting from 5, we can jump 1 step to the left and 1 step to the right. And let's say we jumped 2 steps to the 1 step to the right? So from here we can either again jump 2 steps to the right and 2 steps to the left. If at any of these jumps we find an index with the value of 0, we are returning that. If not, we are returning. If we find the 0, we return true. Otherwise, we are returning false, right? Again, we are solving this problem using dynamic programming bottom-up approach. So what we do is we are creating an array with the size of whatever the size of, let's take another example, right? In this example, so we are taking whatever the sizes of our current array, and we are setting the values to initially for all of them to null. So what we do is our base case, right? If we are checking at each step, we are checking that if we are going beyond in any of these jumps, right, beyond the size of our array, either we are going to the left or to the right, we are going beyond of our array, we are returning false. Otherwise, if we see that any position with the value, any index with the value of 0, we are returning true. And so at each step we are making a recursive call from that position, a recursive call to the left and to the right? So let's go to the code. I think that it will be more clear. So what we are doing here is, so what we do is we are for each step, right? So we are passing our position, and we are passing that from which position we are starting our array and our 2-dimensional array, right? Which is the Boolean. So we are checking that. So in order to not to go to recursively, not to go solve the same problem that we have solved again, if the DP position, if we have already reached that index, so if that's not equal to null, then in that case we are returning whatever the index in that position, right? Otherwise, we are setting the DP position to false, and we are jumping to the left and to the right, and we are setting the position to whatever the value we are returned here, and returning that value. Another problem that we have for jump game is that we are given an array, and we are given a k, which is that how many steps that we can make at the time, right? And we need to find that the maximum value that we can get from this array, moving the k steps starting from each position, right? So for example, let's say that here, so what we can do is we can go either 1 or 2 steps, right? Let's start from the very beginning, and what we do is, again, as a solution, we are creating a DP array with the size of our array, with our size of our initial array, and with size of our initial array, and we are just storing sub-problems here, and we are building up to our solution, right? If we have only one value, let's just start from 1, right? It's a good exercise always to break down to 1 value, 2 values, 3 values, and so on, and expand our solution. So what we do here, so we are taking the first, which is 10, so we are taking 10. So if we have only one value, the value would be 10, right? We are making only one step. For the second one, we can come only from here, so 10 plus minus 5 gives us 5, right? But for the third one, for the third step, so what we have, right? So we can either come from here or we can come from here, which gives us 5 plus 10, 5 plus 5 gives us 5, and 5 plus 10 gives us 15. Yeah, so we are choosing 15, right? So we are choosing 15. And again, for the last one, the same. For the value is 2, so 2 plus either we can come from here or from here. 5 plus 2 gives us 7, and 5 plus 15 gives us 17. We are choosing the 17 as a solution, as a max value, and we are returning that. But what's the problem here? The problem is that for each step, what we need to do is we need to go the k steps back, right? So we need to reevaluate our solutions. So for example, either backward or forward. So what we need to do is we need to go and reevaluate that. Okay, what is the, so for example, let's say at this stage 2, right? So we need to go back k steps. Okay, so 5 plus 2, so 15 plus 2, or 5 plus 2, if let's say k is equals to 10, which means that we need to go the k steps back, right? So how we can solve this, like kind of optimize that part, right? So the first one is we are just using the dynamic programming, and that's the first part, right? But we can further optimize that. For the further optimization, what we do is we are using a DQ, right? So DQ is we can pull from the beginning and from the end, right? So from the first element and from the last element. So but if you think about that, into the problem, so you can see that, okay, so in this case, right, so what we need to do is we need to keep we need to keep the largest element, right? So we don't need to go back actual k steps back. So what we need to do is we need to only keep the largest element from I minus k to I, right? So let's say that we are somewhere down the road, somewhere here, right? So we have hundreds of elements, and what we need to do is we don't need to go back the k elements. We need only that the starting from the certain index, k, whatever the index we are at that moment, right? Minus k. So in that frame, so in that part of the array, we need only the largest element, right? So for example, let's say that we have these 2 values, so we don't need to go back to two steps back. We only need in our DQ store 15, right? So we need to only keep the 15 in our DQ, and whenever that we are considering for the next step, we just need to take this value. That's it. So that's the solution. That's another optimization that we are adding on the top of it. So again, at each step, what we do, and in the DQ, we are storing not the value itself, but we are storing the index, right? So what we do is we are just taking the value dpi nums I plus whatever the largest index value, right? So we are adding to our dp, to our array, to our dynamic programming array. But at each step, what we do, we are going back and we are pulling all the indexes that are less than I minus k, right? So we don't have to keep those indexes. And the second one, so what we do is, as a second exercise, we are removing all the elements that are less than the largest value, right? So whatever is less than our current dp I, so which means that so for example, let's say that we are at the index where the value is 20, right? So whatever is less than that, so we don't need to keep them in our DQ anymore, right? So we are removing, and we are only keeping the value we index with the highest value, and that's our solution. So the first one, at each step we are removing all the indexes that are no longer relevant, and the second one we are removing all the elements that are less than our current element. Game problem that we have is a stone game. So what we are given is we are given a pile of the stones, and we have 2 players, Alice and Bob. So each of them is taking the one pile starting from either beginning at the end, and the one that ends up with the most stones wins the game. So for example, in this case, and Alice starts first, right? So let's say Alice takes 5, and the Bob also takes 5. Then Alice takes 4, and the Bob takes 3. So Alice have 9 stones, and the Alice wins. So in our case, what we need to do is we need to return true if the Alice wins, or false otherwise. So let's take this very simple example. Let's say we have 5, 3, and the 4, right? And as usually in dynamic programming, so what we do, we are breaking down that problem to the subproblems, and we are solving a subproblem and then building up to our solution. So in this case, what we have, right, it's very similar to the idea was, right? The solution was, it's very similar to
the longest palindromic subsequence. So in this case, so what we do, let's take that we are creating two-dimensional array. So in our array, so what we do in our array, what we do is, so let's take the first, right? Let's say that we have only one pile, right? So one, and if the number is so at the end here, right? So what we are returning, if the value is positive, then which means that Alice has more stones than the Bob, we are returning true. If it's negative, then we are returning false. So let's say that we have only one stone, right? Only one value here. Then in that case, so what's that mean? It means that Alice will always win, right? Because Alice starts first, so Alice will always win. So 1, 5, 5, 1, and the 4, right? So how about, let's say we have two stones, right? Let's say that we have either 5, 3, or we have 3, 4, right? In this case, what we have is Alice starts first, so Alice takes 5, and the Bob takes 3, so Alice wins, right? The difference is 2, right? So we are adding 2 here, and the next one, so what we have, 3 and 4. Again, Alice starts first, takes 4, and the Bob takes 3, so we have 1, and we are adding 1 here, right? So now we solved the subproblem. We solve the problems when we have only one element. We have two elements, right? Now we are solving a problem when we have three elements. If we have three elements, so what are the scenarios there? The scenarios is that, for example, let's say that for this scenario, right? For this scenario, we are adding one more element to the right. So we are adding one more element to the right. So which means that if the Alice will start with the 4, right? Then the Bob also will. Every player will take the maximum stone, right? Will play optimally. If the Alice starts with the 4, then Bob will start. So then Bob will take the value that the Bob will get is 2. So basically, what it means that at this point, right? If we have three elements, we are taking whatever the value we have here minus whatever the maximum value we are getting here, right? So 4 minus 2 gives us 2, right? And if we, let's say, take another scenario, so we are adding one more element to the right, so we are adding one more element to the left, so which means that the Alice will take 5, and the Bob will get at the end, the result for Bob will be 4, right? So the result for Bob will be 4, so which means that because Bob also will play optimally, right? So, and the difference gives us 4, right? Gives us 4. So now what we are doing, we are taking whatever the maximum is 4 and the 2, which means that whatever the maximum gives us, whatever the maximum of 4 and the 2, in this case we are taking 4 and we are returning 4, right? So why we are doing that? Because from our perspective, we are trying to play from the Alice perspective, right? Alice tries to play as optimally as possible. So we need to find that is there any way for Alice to win? And for that reason, we are taking the max value here, right? So what we do at each step, right? If we put that into the code, into the formula, so what we are doing is, and we are maintaining two pointers, right? I pointer and the J pointer. So for each pointer, so what we do, either we are taking J pointer, so which means that in this case we are taking 5. If we are taking 5, then 5 minus whatever the dpi plus j, so whatever the value we are getting here, right? dpi plus j from 3 to 4, right? So whatever the max value is here, because Bob also will play optimally. And if we are starting from here, if we are starting from the end, then in that case we are so what we do, so we are taking dpi j minus 1, right? So if we are starting from here, so then we need to get whatever the minus whatever the value we have here, right? So, and we are taking the maximum of it. And if we go and look at the formula, so that's exactly what we are doing. So what we do is at each step so at each step, so what we do, we are checking that so we have k is equals to 2, and we are doing with the 2 increments, because we are taking the pointers at the beginning and at the end, right? So what we do, we are checking what we have just seen earlier, right? So we are either taking that pile from the beginning, or we are taking from the end, and minus whatever the subproblem that we have already solved, and we are taking the maximum of it, and at the end we are, if that value at the end is
for I and j is positive, then which means that the Alice wins at the end. Otherwise, we are returning false. Alice loses. The next problem in the game theory and optimization pattern is the coin change. In the coin change problem, so what we have is we are given a coins. For example, let's say that the 1, 2, and 5, and we are given an amount, and then we need to find the minimum number of the coins that we can use in order to make that amount. So how we are going to solve this problem? Again, we are using a dynamic programming bottom-up approach. So what we do is we are creating a DP array with the size of the whatever the amount is plus 1, and if we are filling that array with the values of the amount plus 1, right, the maximum value that we can return. And for the DP0, so for the value of the 0, we can make it with the 0 coins, so we are setting that value for this to 0. So what we do at each step, right, so we are going for each amount. So what we do is we are considering each coin, right, so here we are taking that if the coin j, so which means that if we can apply that coin, if let's say that we have only amount is equals to 3, so we cannot apply 5 there, right? If we can apply that coin, so what we do? We are taking either whatever the value is that at that position, right? So for example, let's say that at 5, right? Either whatever the value at that moment in that position, minimum, or we are going 5 steps, or we are going whatever steps ahead, right? Whatever the value of the coin, that steps ahead from the I, and we are taking the DP value there plus 1, because we are using the 1 coin right here. And at the end, we are just returning whatever the maximum value that we are getting, whatever the minimum value that we are getting using all of these coins. So now let's go to the next one. The next one is a best time to buy and to sell stocks with the cooldown. In this problem, what we have, right? So what we have is what we need to do, right? So we're given an array, and for each, the value of each index represents the stock value, right? So we can do 3 things with the stocks. We can either buy or sell, or if we just sold, so we need to have 1 day cooldown. So for example, if we take this array, if we are the maximum that we can get from this array, if we buy from at the first day, sell at the second, then at the third day we cannot buy, right, or sell. We should have a cooldown. So we have a cooldown, and then we are buying at the 4th day, and we are selling at the 5th day. So we have the profit of 3, right? And we need to find that the maximum profit that we can get from this array. So how we're going to solve this problem? We are going to solve this problem using not the bottom-up approach, but the top-down approach. And for that, let's consider the scenarios, right? What are the scenarios? The scenarios is that for the day 1, what are the options that we may have? The first one is that if we are just starting and we have 2 variables, let's maintain, right? Bought and the sold, right? Both of them are false. We are just starting. The first option that we have, we can buy this at the first day. In that case, our total value will be -1. And at the second day, what we can have, right? So we can skip, right? So that's another option. At the second day, again, what we can do, right? The second day, so what we can do is, if we already bought, so then our bought is true, right? We set that value to true. Then in that case, if that is the case, then so what we can do, we can either sell, right? So if we are selling, then our total value is +2, and we are setting that to true, or we can just hold, right? So the second day. So the third one, so another option for the day 2, so if we let's say didn't do anything at the first day, so we are buying, and we are then here setting the buy to true, or we are just skipping, right? So that's another option for the day 2. For day 3, so what options we have? If our sold is true, and we cannot do anything here, so we have a cooldown, right? So another option, if we bought at the first day or second day, and so we are, let's say, selling, then in that case, so what we do, we are selling, and so we are selling, and we are setting our brought to false and sold to true, or we are just holding. And or if we haven't bought anything, then in that case if we are buying, we are setting bought to true, and or we are skipping. This is all the options that we have for case if we have only 3, let's say that if we have not 5, but let's say that we have the three values in this array, right? 3 indexes in this array, but even if we have more, let's say even if we have more, we don't have more than of these 3 options for all the cases. So to do that, to apply that to our logic, so what we do here is we are generating a tree, so for all possible scenarios, right? And we are taking at each step, we are taking the max profit. So what we do is, and in order for us to not to solve the same problems that we have solved earlier, so what we do is we are storing our whatever the problems that we have solved for the day, bought and sold for that scenario that we have seen earlier, we are storing that in our memo, right? We are storing that in our memo. If we have solved that problem already, we are just getting that from our cache. So again, we have we have 2 options. If we bought, so we are generating tree for 2 possible scenarios, and we are taking the maximum profit, whichever gives us the maximum profit. If we have sold, so we are, for one scenario is when we have a cooldown, and another scenario is that we are buying or we are skipping the profit, right? And we are taking in the maximum of it. So whatever the maximum is returned, we are returning that as a result. So now let's go to the next one, and the next one is that the partition array for maximum sum. In this problem, so what we do is we are given an array and we are given a k. So what we do is we can, in our array, so what we can do is we can select the number of the elements and convert them to the maximum number in that subarray. So for example, let's say that we are choosing first 3 elements and converting them to the 15, because 15 is the maximum number in this subarray. And the same what we are doing at the end. So for the 2, 5, 10, so we are choosing another subarray and we are converting all of them to 10, and we are returning the whatever. So what the end goal is, we should return the maximum result, right? So maximum result after converting the k elements, k subarrays with the k elements to the maximum element in that subarray. So how we're solving that problem? So there are 2 ways actually how we're going to solve this problem. The first one is that with the bottom-up approach and the top-down approach, and we can compare those, right? So for the bottom-up approach, the solution is standard, right? So what we do, we are creating an array with the size of our DP array with the size of our initial array, right? So here we have an array 5, 15, 7, and 9, right? Let's step by step go and so let's step by step go and solve the problem and see that how exactly solution works out. So first, let's say we have only 1 element. If we have only 1 element, for the first one, the value is 1, right? If we have 2 elements, so what are our options here? Our options here is that in k is equals to 3, right? So we can choose 3 elements. So either we can choose we can take one of the elements. So for example, if we can take one, let's say that we can take the 15 as a maximum in this subarray, right? So 15 plus 1 gives us 16, right? Or we can convert everything that is in this subarray to 15, right? So 16 and the 30, whichever is the maximum. Maximum is 30, so we are converting that to 30. Now we are going to the next one. In the next one, again, what we are doing here in the next element, right? The next element, the solution is the same, right? So we are taking 7 plus whatever the maximum value up to this point, right? That's the first one. Or we are taking whatever the maximum value in this among these 3 and converting that. So 37 we are comparing with the 45, and the 45 is 45 is more than 37, so we are adding here. Now let's go to the next one. Next one is 9. So 9 is, we can consider either this element, and in that, if we're considering this element, then in that case we need to take whatever the maximum value up to here, right? Up to here, the maximum value up to here is 45, or we can consider these 2 elements, whatever the maximum here, or these 3 elements, whatever the maximum there, and take whatever the maximum until this point. So for example, let's take these 3 elements, 15, 7, and 9. Maximum here is 45. So for maximum here is 15. 15 multiplied to 3 gives us 45. Let's say we are converting all of them to 15, right? Plus 1, 46. So 46 is less than 54, so we are returning the 54 as a result, right? And the solution wise is the same.
So at each step, we are either choosing the element or we are choosing the maximum within that frame, within that subarray, multiplied to the j, right, to the number of the elements that we have selected, right? Let's say that we have selected in our first case, right? So we have selected 2 elements, which means that we are multiplying that to 2, and we are going to 2 steps back and taking whatever the dp maximum value is there. So in our case, we are at the last element. So what we do, right? Let's take the last element in our case. So what we do is, in our case, we are taking either the value what we have at last, right, at the dpi at there, whatever the value we have there, or we are taking that value dpi minus j, so we are moving j steps back. So we are moving j steps back, which means that we're here, right, and the multiplying j multiplying to whatever the max value is, right? So in our case, since the value is equals to 54, right, so since the value is 54 is more than 46, so we are choosing the 46 here. That is related to the all problems that are optimization and the maximum and the minimum value. And so optimization, which is that whenever we have a problem that requires to find the maximum or minimum, or that the game theory related problems, right? Let's sum up so far what we have learned. So what we have learned is that in dynamic programming, so I have several patterns that I follow, and I'm sharing that with you. So the first pattern is that the quintessential bottom-up approach which is when in the requirement to the problem, in the input, we are already given the array that we can use to store our subproblem to build up our solution. The next one is that the string manipulation problem, and in the string manipulations problem is basically finding the longest substring that is palindromic, and the similar kind of problems that we have seen earlier. In those problems, we are not given the array where we need to store the subproblem, and that's the biggest challenge when we are solving the dynamic programming related problems. So the second one is that the string manipulation related problems in dynamic programming. So for that, we are usually using either array or two-dimensional array. And the third one is that we have just reviewed optimization and the maximize minimize optimization, which means that in the problem statement we are asked to find the maximum or minimum or maximize or minimize our result, or game theory related problems such as the stone game, or let's say jump game, and so on. So the last one that we are going to review, last pattern that we have, is a top-down solution. Top-down solution is very easy to implement. So unlike the all others that come before, which is the bottom-up approach, these problems, top-down solution is very easy to implement, but the most of the time they are not as optimal as the bottom-up approach. But the problem that you solve using the top-down approach, using the bottom-up approach, the same problem can be solved using the top-down approach. For example, let's take this example that we have just solved, right? Partition array for maximum sum. We solved that using the top-down approach. So the same problem we are using, we have in the previous example, right? So we have solved the problem using the bottom-up approach, but here we are solving the same problem using the top-down approach. So again, let's take the same example that we have and let's try to solve it using the top-down approach. So here what we have, right? So for the top-down approach, we need to find so we have a function. We need to find the maximum for 1, 15, 7, and 9, exactly the same that we have solved before, right? So what we do is we are recursively trying to find 1 plus maximum 15, 7, 9. So for this subproblem, and then for 15 plus to a smaller subproblem, and then we are trying to solve for the 7 plus whatever the maximum is for this subproblem, and then we are building up to our solution, right, for the top down. So what we do for the max 9, it's just will return us 9. We have only one element, right? And also what we do is we are creating an array here. In our array, we are storing our temporary solutions, right, that we are going to use, right? So not to solve the same problems over and over again. For the index 3, right here, So what we have for the index 3, the value is 1. So we are returning back this, so we are returning back the value. And the next one, so what we do, right? So maximum is 9. So 7 plus 9 gives us 16. So now we are solving the problem we solve for maximum 9. Now we are solving for the max 7 and 9. 7 and 9 is that, so 7 plus 9 gives us 16. That's the one is 16. And another one is that another case, right? We are just taking this elements separately, 2, 7, and 9, and whatever the maximum here. Maximum here is 18, so we are adding 18 to our, so we are choosing between 16 and 18 as whichever is the maximum. Maximum here is 18, so starting from the index, the value is what? The maximum value is 18. Now we solve for this problem. Now we are building up to our solution, right? Now we are solving the problem for 15 plus maximum 7, 9, right? So the value that we have returned here is 18, maximum value. 18 plus 15 gives us 33. That's one option. Another option is that we are choosing that 7, 9, and the maximum 9, right? Maximum 9 already returned us 9. So, and the maximum between these two, 15, 7, maximum between these two gives us 15, right? So 15 multiplied by 2, 30, 30 plus 9, 39. So here we have 33, 39, and another option is, since the k is equals to 3, so we are taking all of these elements, right? 15, 7, and the 9. So 15, 7, and 9, the maximum here is 45, so we are comparing all the results, right? 45, 33, and here what we have, right? 39. The maximum here 45, so we are saving that value also in our array. Now we have solved all the subproblems, right? So now we are solving for 1, right? So for 1, again, we are choosing the same. So what we do is, for the max 1, 15, 7, 9, right? So we are choosing 1 plus maximum these two, right? 1 plus maximum, 1 plus maximum, whatever the maximum this one returns us, or we are choosing that the 1, 15, and whatever the 7, 9 returns us, right? But the 7, 9 we have already solved, right? It returns us 15, it returns us 18, and then now it returns us 18, so we are taking that from our array, right? So we don't solve that problem again. So as you can see, and at the end we are returning whatever the max value here, right? So as you can see, the same problem, we have solved that using the bottom-up approach, top-down approach. In this case, the complexity, time and space complexity of solving these problems are the same, but there might be a case when usually the time complexity for solving bottom-up approach is, or overall, let's say, it's more optimized way to solve a problem, but it's not always easy to structurize and solve the problem using the bottom-up approach. So the code-wise for the top-down, right? So what we have here, is that, again, we are creating a memo. We are storing our results starting from the certain index, and if we have already solved that for the starting from certain index, we are returning that value and whatever the maximum amount that we are getting for that index, right? So we are solving that here in our memo. Now let's go to our next problem. Next problem is that partition equal subset sum. This is probably one of the most recognized and one of the most solved problems, partition equal subset sum. So what we have is here, so we are given an array, right? Let's say that we are given an array 1, 5, 11, and 5. So we need to find that whether or not we have this array can be divided into two equal subsets, which means that the sum of those subsets will be equal, or some of those subsets will be equal to each other, right? So for example, let's say we have 1, 5, 11, and 15, and so we can divide them to 2, so we can divide that to 1, 5, 5, and another one is 11. So 1 plus 5 plus 5 gives us 11. 11 is equals to 11, so we are returning true. Otherwise, we are returning false. Again, how we are solving this problem? The first one, we are taking the total sum. Total sum is 22. If that sum is odd, so which means that it doesn't matter in which way we are splitting that, we cannot make it two equal subsets, right? So we are returning false. If they are equal, then we are choosing a target sum, which is the half of our sum, and we are searching for the subset which is equal to this target sum. If we find that subset, then which means that the another half, then another values that we haven't included in these subsets, they are they will make another equal part of the subset, right? So what we do in top-down approaches, if we are using a top-down approach, the biggest challenge here is that when we need to generate a tree, right? So generating a tree is a challenge, and we need to know how exactly we are doing that. So for example, in this case, we are first generating a tree for 1, for 1 and 5, and then we are, for this branch, we are generating for 1, 5, and 11. 1, 5, and 11 more than 11, so we are backtracking from here, right? So then we are generating for the next one, for the 1, 5, right? So for the 1, 5, we are generating, so we are generating 1, 5, 5. 1, 5, 5 is equals to our target sum, so we are returning true here, right? But this solution is not enough, because in this case, what we need to do is we need to optimize our solution, right? This is the plain backtracking solution. So what we need to do is we need to add here memo, right? We need to add cache here. So what it means that, for example, let's say that we are solving our problem and we are at this point, we are at index 2, and the target sum is equals to 6. So which means that we need to find that starting from the index, we have already considered these scenarios, right? Starting from the index 2, do we have any subproblem where the value is equals to, where the sum is equals to 6, right? If we have already solved that subproblem, whether or not that exists or does not exist, so we are saving that to our two-dimensional array, where the first one with the x-axis is index and the y-axis is the sum. So we are storing whether or not we have solved that subproblem. If we have solved, so we are returning that from the cache instead of the solving that subproblem again. As you can see here, so we are passing here our nums, target sum, temporary sum, index, and our two-dimensional array, right? So we are checking that if that is not equal null, so which means that we have solved that subproblem, so we are returning the value. If we did, so we are putting here that the include and the exclude, so we are backtracking, generating a tree, and at the end we are returning whatever the value is there for that specific index and the temp sum, which is, in our case, it will be that we are returning for our whole array and for the target sum. And now let's go to the next one. The next one is that this is one of my favorite problems that is out there, which is that the shopping offer. So in this problem, what we have, right? So we are given prices for the items, and also we are given how many of those items we need. So for example, let's say that we need item 1 and the 2. Item 1, the price is 1. For the first item, the price is 2. For the second one, price is 5. And the needs is, for the first item, the need is 3. For the second one is 2, right? So that's our purchase, and also we have a special. So what it means? It means that let's say that the 3 of the first item and the 0 of the second item is for price 5, right? And the first one of the first item and the 2 of the second is for price 10. So what we need to do is we need to find that to spend least amount of money, right? So to list the least amount of money to buy everything that we need, right? So what we are going to do, so what's the solution in this case? Let's just start from the beginning and to see how exactly we are solving this problem, right? The first one is what we do. We are just calculating the direct price, right? Direct price is that, let's say, 2 multiplied by 3, right, gives us 6, and the 5 multiplied by 2 gives us 10, so 10 plus 6 gives us 16, so that's the direct price. So meaning that without using any specials. Can we do better than that, right? Can we, let's start to apply our specials. So we are applying our first special. Our first special is 3 of the first one, 0 of the second one, gives us 5. Also, when we are applying a special, it should not exceed the amount that we need. For example, let's say that this one is, let's say if this value was something like 6, so we cannot apply this because our need is 5, and we are taking the special that has 6, right? So we cannot take more than we need. So we are applying the first special. If we are applying the first special, so 3, 5, and 3, 0, and 5. So we're applying the first special, so what we have, right? So now our need is 0, 2, right? 0, 2, because this one is covered, right? So we are taking from our needs 3, so now we have a 0, 2, right? Now we need 0 of the first one and the 2 of the second one. So then again, we are trying to apply more specials because we can apply these specials as many as we want. So can we apply more specials here for the 0 and 2? No, we cannot. So can we apply second special? No, we cannot. So we are backtracking from here. So the 5 plus the 5 we paid for the special, and again, let's say calculate direct price. 2 multiplied by 5 gives us 10, so 15. 15 is better than 16, right? So we are paying the less price here. So that's the first one. But that's how we are doing, right? So we are generating a tree and we are applying that. Can we apply those specials to our particular case as many times as it's possible? If not, then we are returning as a result the minimum price, right? So we are exploring all the options and we are exhausting all the options and we are returning whatever the minimum price is. But there is one caveat here, and the caveat is that let's say that we are solving a subproblem, right? So we don't have any specific scenario for this small example that we have, but let's say that we have a larger example and we have already solved that for the needs 5, 4, and the 2, the smallest amount that we need is 50, right? The smallest amount, we need 50, and we are going to solve the same problem in another branch, right? So for these needs 5, 4, and the 2, so we again will try to solve the same problem. So what we need to do is we are creating an array, we're creating a hash map memo, right? So key is our needs and the value is the lowest priced for those needs, right? So for example, for our case, we are going to store 0 and the 2 right here and the minimum value of 10 to reuse that, right? That's it. That's the solution. So what we do, right? So we are using a backtracking. We are generating all possible solutions, the same as in the previous one, right? So we are generating all possible scenarios and we are storing the subproblems to our cache, to our memo, in order to reuse that later and in order to not to reuse the same problem again and again, right? And this is the solution. So we are creating a DP where we are storing temporary our values, and here we are applying our, so we are trying to apply our specials as many times as possible in order to get the lowest price. So we are generating all the possible combinations for that, all the possible combinations for our input. So that's it. That was the last one that we have, that I was planning to include in our dynamic programming patterns video. So again, to sum up, so what we have here, right? So for the dynamic programming, it's again one of the hardest problems out there to solve. And I have identified more patterns. If you have identified more patterns that I haven't included in this video, please share them in the comments below. So what we have is the first one is, right? The first one is the quintessential bottom-up approach. Is basically when in the input you are given the already array and the array or two-dimensional array that you can use to store your subproblems to build up to your solution. The second one is the string-related problem, string manipulations problem. As you can see, that you have seen, you can find that earlier in the video. So we tried to go over but let's say that the most popular string manipulation problems. So as you can see that the solutions for those is very similar to each other, but in that case you need to put an extra effort in order to come up with the exact data structure. Either it's an array or two-dimensional array where you are going to store your subproblems. The next one is that optimization problem, find the minimum, find the maximum, or let's say that it's a game theory related problems, and there again we are using the bottom-up approach. And the last one is the top-down approach, so we are using the recursion or backtracking. So we are generating all possible solutions and we are storing those solutions in the cache in order to not to recalculate, not to solve the same problem that we have solved again, right? So again, for all those videos, for all those problems that we have reviewed here, I have the separate solution for all of them in my channel. If you go to my channel, I will also include it in the description. If you go to my channel to the dynamic programming playlist, the problems that we have reviewed here, they are exactly in the same order that we have reviewed in as part of that playlist. So you can review that, leave your comments, and if you have more questions, or if you think that in these patterns I should have added more, probably if you have solved enough dynamic programming problems, you have identified your own patterns, you can share that in the comments. Okay, that's it for today. It's a pretty long video. I think that it's more than an hour, so I hope you like it. I hope you find it useful. You will find it useful, and if you have any questions, again, leave in the comment. See you next time. Bye.